Hi, welcome back everyone. I hope that you all had a great Thanksgiving break. We're going to jump right into the physics, talking about something called work and how it relates to forces. So what the heck is work? Usually when we think about work or talk about work, we think about a career or a job we have to do. But there is actual physical meaning to the word work. Work is what's done to an object when a force is applied to move it some distance. So if we have a big old pile of coal over here that this guy is moving, he is applying a force with his shovel to move that coal some distance. He is physically doing work. The units of work are something called joules, and we abbreviate the joule with a capital J. It turns out that joules are a compound unit, just like Newton is a compound unit. A Newton is a kilogram times a meter per second squared. A joule is a Newton times a meter. And given the definition of what a joule is, we can actually figure out the basic equation for work. So like I just said, joules are a unit for work. Newton is a unit for force. Hopefully most of you remember that. And a meter is a unit for displacement or distance. So work is equal to force times distance is the general shape, I guess, of the equation for work. But it's a little more complicated than that. It turns out the work done by a constant force, not changing, is defined as the distance moved multiplied by the component of the force in the direction of displacement. Now, what the heck does that mean? Well, mathematically, that means our equation looks like this. Work is equal to the force applied times the displacement times the cosine of the angle at which the force is applied. So let's look at this picture as an example. This girl appears to be pulling a very heavy box across the floor. The force she applies is at an angle to the horizontal. But the box doesn't move up at that angle. It moves straight across the floor, this way. So what we need to do is only worry about the portion of the force she applies that's in the same direction of the movement of the box. So what we can do is take a little pretend flashlight and shine it down on top of the force that she's applying. And whatever is under that shaded region in the direction of the box is the amount of force we're concerned with. So this amount right here is actually what takes the place of F cosine theta. Now, it does get a little tricky because this involves triangles and trigonometry, but I think you can all do it. And just a little bit about cosines that will probably help is remember the big thing here is SOHCAHTOA. Gotta remember SOHCAHTOA. So if we have a triangle and our angle is right here, the cosine of the angle is the adjacent side. And the sine of the angle is the opposite side. But we're not concerned with the sine of the angle for this equation. We're only concerned with the cosine. So the horizontal portion, or the portion that is right next to your angle here, is going to be the cosine portion of your force, as long as your force is the hypotenuse. So if we apply a force at an angle of 0 degrees to the horizontal, that means our force is horizontal because the angle is 0. So that means the entire magnitude of this force is the cosine of the angle of this force. An easier way to see that is if you plug the cosine of 0 into your calculator, it turns out to be 1. So when you plug that into your equation, work equals force times distance cosine theta, work equals force times distance times 1, work equals force times distance. So if the force applied is already in the direction of the movement of the object, the cosine of 0 goes away and you're left with force times distance, because all of that force is being put into doing work on the object. However, the opposite is true if we look at an angle applied 90 degrees or perpendicular to the direction of motion. So if this motion is moving along the black arrow to the right and you apply a force perpendicular to it, you are not doing any work at all, because there is no part of this blue arrow of the force you apply that is in the direction of movement. And if you put this in your calculator, cosine of 90, you'll see that it equals 0. So when you plug that into your equation, work equals force times distance cosine of the angle, this all goes to 0. And the math doesn't lie. It turns out, even when you're applying a force to something, if you are not applying that force in the direction of movement, if you're applying it perpendicularly or at a 90-degree angle, you're not doing any work on it. So for example, this guy is carrying a bag of groceries. Gravity is trying to pull that bag of groceries to the ground, and hopefully he doesn't have any eggs in there, and hopefully gravity doesn't win. And he has to apply a force upward to counteract gravity. So he is applying a force to this grocery bag, but he is moving to the right. So he's applying a force vertically, but he's moving horizontally. And this makes a 90-degree angle. So it turns out, even though he is pushing on this bag and he is moving it, he's moving it perpendicular to the force applied. So he is doing no work. The work on this grocery bag is 0 joules. You only do work on an object when it moves. If the object does not move, or if it moves perpendicularly to the force applied, there is no work done. So let's try a sample problem. There's a 65-kilogram firefighter, and he climbs a flight of stairs 20 meters high. How much work is required to do this? Well, remember, work is equal to force times distance times the cosine of the angle. So first of all, what is the force applied here? When this firefighter is climbing a flight of stairs, what force must he exert? Well, in order to get up the stairs, he has to at least push as much as gravity is pulling down on him. So the minimum force required to lift him is equal to his weight. And remember, weight is the amount that gravity pulls down on a mass. So his weight is going to be his mass, 65 kilograms, times the acceleration due to gravity. So we already know the force he needs to apply. And it turns out we also know the angle at which he's moving. When you push up off the stairs with your foot, you are pushing straight up and down. And the direction you want to move in is also straight up and down. So the angle between these two, the displacement where you move to, and the force applied is 0. So if we plug both of those in, we get the work required is his weight times the displacement times the cosine of 0 degrees. So we have 60 times 9.8. It should be 65 times 9.8, by the way. His mass is 65. Times the 20 meters that he climbs up, and then the 1 takes the place of the cosine of theta. Remember, because if you put cosine of theta in your calculator, you get 1. And it turns out it takes this firefighter 1.27 times 10 to the 4 joules of work to climb these stairs. Now, work is a vector quantity. And that means it not only has magnitude, but it also has direction. So it is possible to have negative work done on an object. For example, work done by forces that oppose the direction of motion, like friction, will be negative. And it turns out centripetal forces, or forces that keep something moving in a uniform circular pattern, do no work, ever, because they're always perpendicular to the direction of motion. So if you look at the Earth and the Moon here, the Moon is moving straight to the side. It moves tangentially to its orbit. But the force keeping it in this orbit is pointing straight in toward the center, at the Earth. The force of gravity from the Earth on the Moon is what keeps it moving in this circle. And because these make a 90-degree angle always, the Earth does no work on the Moon. Which is kind of a strange fact, but it's true. So when you're solving work problems, do these steps. It will help make everything clearer, hopefully. So the first thing you want to do is draw a free body diagram. You need to choose your object and draw a free body diagram of all of the forces acting on that object. Then you choose a coordinate system, and that means choose an x and y axes. Most likely your x will be horizontal and your y will be vertical, but that doesn't have to be the case. You can turn it to fit whatever is convenient for your problem. The third step is to apply Newton's laws to determine any unknown forces. And you're especially going to focus on Newton's second law here, F equals ma, to find the magnitude of some of these forces. Then you can find the work done by a specific force. Then to find the net work, you either find the net force and the work that it does, or find the work done by each force and add them together to see how they work. Remember, you can have positive forces and negative forces, so some of them might cancel. So keeping all of these steps in mind, let's try a sample problem. How much work does a man do horizontally, pushing a 160 kilogram crate 10.3 meters across a rough floor without acceleration, if the effective coefficient of friction was 0.5? What is the work done by friction, and what is the net work on the box? Well, the very first step, remember from the last page, is to draw a free body diagram. So the object that we are concerned with here is the box. And we want to know what forces are acting on this box. Well, we have the force of gravity pulling it down, and we have the normal force of the floor pushing it up. We have the man pushing it to the left, force of the push, and we have friction resisting that push to the right. So we have 4 forces here. And just looking at this, we can actually determine a little bit about the magnitude of these forces. So the box moves horizontally. It does not move up and down at all, which means the acceleration in the y-axis, right? Gotta find a good color here. This is y, and horizontal is x. The acceleration in the vertical axis, the y-axis, is 0. And because it's not accelerating, we know that these two forces must be equal to each other. The amount the floor pushes up on the box and the amount that gravity pulls down on the box are the same. And it turns out the same thing is true about the force of the push the man is applying and the force of friction. Because this box is moving across a rough floor without acceleration. If there is no acceleration, then velocity is constant and the forces must be balanced. So now that we know that, we can start looking at this quantitatively. So the very first thing that we can do is actually find the magnitude of some of these forces. And we'll use that, to figure that out, we will use Newton's second law. The sum of the forces is mass times the acceleration. And what I really want to look at is the sum of the forces in the x-axis, in the x-coordinate plane, because that is the direction of the movement of this box. So the sum of the forces in the x is the mass times the acceleration of the box. The two forces we have in the x are the force of the push and the force of friction. But they go in different directions. So one of these has to be negative. Typically we define to the right as being positive and to the left as being negative, but I'm actually going to do the opposite. I'm going to say going in this direction is positive for this problem. So our force of the push is positive and our force of friction is negative. And this is equal to the mass times the acceleration of the box. Well, we know the mass of the box. It is 160 kilograms. And we know the acceleration of the box. If this box is moving at a constant speed, without acceleration, the acceleration is going to be 0. So the force of the push minus the force of friction is equal to 0, which tells us the force of the push has to be equal to the force of friction. And we already determined that on our force diagram. But now that we have this, we can actually figure out how strong the force of the push must be. So remember, the equation for the force of friction is the coefficient of friction times the normal force on the box. But from our force diagram and reasoning through, we know that the normal force is also equal to the force of gravity. So the force of friction can be calculated by multiplying the coefficient of friction times the force of gravity, or the weight of this box. So now we can plug some numbers in. The force of friction is equal to 0.5, which is our coefficient of friction, times the mass of the box, 160, times the acceleration due to gravity, 9.8. Remember, whenever you're finding the weight of an object, you take its mass and you multiply by the acceleration due to gravity, which on Earth is 9.8. So when you do all this out, you find that the force of friction is equal to 784 newtons. Okay. So we know how much the force of friction is. But what does this tell us about the force of the push? Well, remember from up here, the force of the push on the box is equal to the force of friction because this box is not accelerating. So this also has to be equal to the force of the push. The only difference is one of them is going to be negative and one is going to be positive. So if we do the next step here, now that we know the force of the push, we can figure out the work done on this box. In order to do that, we have to use our new equation. Work is equal to force times distance times the cosine of theta. The force being applied to this box is 784 newtons. The distance it moves is 10.3 meters. And the angle between the movement of this box and the surface is 0. The box moves horizontally, it moves parallel to the surface. So the angle is 0. When you calculate this and plug 784 times 10.3 times the cosine of 0 into your calculator, you get 8,075.2 joules. And because this is moving in our positive direction, this is a positive amount of work. So now the last two parts. What is the work done by friction? Well, the force of friction is equal to the force of the push. The only difference is one is going to be negative. So if you have the box moving the same distance at the same angle with the same magnitude of force, the work done by friction is going to be exactly the same, just in the opposite direction. And this is the work done by the push. So, what is the net work on the box? Well, if this guy is pushing with 8,000 joules to the right and friction is pushing with 8,000 joules to the left, we add the work of the push times the work of friction. And because they are the same magnitude but one is negative, the net work done on this box is 0. So now it's your turn to try a couple of these for homework. So go ahead and look over these problems and try and answer them to turn them in the next time I see you. Number 1, an Olympic shot putter can apply a force to a 2 kilogram shot put such that it constantly accelerates to 10 meters per second from rest in 1 second. His arm is exactly 0.7 meters long. What is the force he applies and what is the work done on the shot put? And number 2, if I'm carrying a laundry basket 10 meters down the hall and I have to apply a force of 25 newtons to the bottom of the basket to keep it from falling, how much work am I doing to move the basket down the hall?